Okay. Okay, good afternoon, everyone. Last week, I think we have introduced the we call the reduction of order, the techniques in higher order derivatives. So firstly, I introduce you a practical way to solve the higher derivative, especially for the second derivative, a second order differential equation. So we are substituting y with a function u and then the y1. So the reduction of order will be completed if we know first, of course, the differential equations, which usually the second order, and then we also know y1. So we know half part of the solution. So we are going to find another one. Okay. So how do we find the another one? First, we are going to set up this new proposed y equation. So we call this proposed for y2, and then we try to plug in this y. Okay. So we differentiate twice, and then we plug in into our equation. So we plug in into differential equation, and then the goals for this equation is to have this we call this is the linear differential equations when we are dealing with another w here to substitute this u prime. Okay. So the deal is we substitute this ux y1, we get another expression, and this expression we force out to reduce the order. So the reduction of order starts from here. That's why we call this reduction of order. So we reduce the order, the second order, to be linear. Okay? And then we can solve this through linear differential equation. Okay? So I hope you're still familiar with the linear differential equations. Okay? Now, secondly, if we took the we barely simplified the linear differential equation and we get the direct form. Okay, I will just skip this process and we get the direct forms that is y2 equal y1, and then you have this integration. This is actually from the linear differential equation when we multiply with integrating factor and then we integrate, right? So this is from the integrating factor. Okay. So there are at least two approaches when you deal with the questions. The first approach is when we know how to make out the equation. So for example, this one. When we wrote the standard form, and then we can identify clearly that this is okay, this will be P, and then we can just plug in the other components. This is y1, this is P, okay, 3 over x. And if we can deal with this, then you can apply this formulations easily, right? But what happens if it's not easy to be integrated? Then you can just substitute using the first method. So using y equal ux and y1, substituting, and then from there actually sometimes some differential equation will be better to be solved through that way, okay, rather than this direct form. But some of the differential equation may be faster to be solved this way. Okay? So I think I will give you some examples to try the method. Okay? So we have differential equations. It's asking y2. Let me give you two example. Another example is This is also asking about y2. You can try. Maybe you can try with this equation first. This one. If it's maybe too complicated, well, you can just substitute. You can try this formulation. For the second question, perhaps at the end, you'll see the proposed solutions have some components, and actually y2 is not all those components. I will explain it. What will be for y2. If this is too difficult, maybe just substitute. Maybe just substitute. Substituting with ux and y1 is the safest way to avoid any mistake on the integral. So first you need to substitute, then try find this y double prime using that substituted, and then try to see the new equation, new expression, and then reduce the order, finding another substitute. Maybe first using u, and then maybe the second part using v or using w. And then after substituting, take linear differential equations and then revert back to the original equation. Okay, perhaps let me get through. Okay, let me get this first questions. Let me write something here. Okay, so first perhaps we could let y is ux and then y1 is sine 3x, and then differentiate and takes product rule, so 3ux or maybe just 3u and then cosine 3x plus u prime sine 3x, and then derive one more time. That will be u double prime sine 3x should be plus 3 and then having cosine 3x, but let me write that. And then this also have the 3u prime cosine 3x. And then lastly we have negative 9 u sine 3x. Or we could combine this and write 6u prime cosine 3x minus 9u sine 3x. Okay. Okay, now substitute to our questions here, the equations. So y double prime is all this. So let me write cosine 3x minus 9u sine 3x. Okay. And then plus 9 of u sine 3x equal to 0. So we are going to cancel this out. Okay. So this will be y double prime, this long prime, and this is y. So we have u double prime sine 3x plus 6u prime cosine 3x, right? I think we can simplify u double prime divided with sine 3x, and we have 6u prime, and then cosine divided by sine is the cotangent, so we can write cotangent. So cotangent 3x equal to 0. Okay, now you need to be aware that when we have this kind of situations, this is a second order. So this is second derivative, first derivative. When we already have this equation, this is one step closer to reduce our order. So we can substitute this u prime so that we are going to reduce this second order to first order. Okay. So we can let let's say another variable. We can say the w, or we can say v, any variable you can think of. But let me just write w. So let w is u prime. So when we have w prime, it's u double prime. Okay. So we can write down our equations. W prime plus 6, let me write cotangent in the front, and then u prime becomes w. Okay, and equal to 0. So we can make out our product form. It's supposed to be w multiplied with something that should be resulting in cotangent 3x. So if you want to take guesses, so it could be, so cotangent is
cosine 3x over sine 3x, right? I think we need to take integrating factor first. Is e, this is cosine 3x sine 3x dx. I forgot to multiply with this. Oh, this is 6, sorry, 6. So cosine 3x over sine 3x. What is the integral of the cotangent? I think we can just do some substitutions here, right? We can substitute let's say sine. So du, or maybe cosine. I think cosine is also okay. So dx is negative. Okay. Oh, it should be sine. To make it to cancel out, right? Yes. Hmm? 1/3. Is it correct? Is it correct? Yeah. Sure. Yeah, also, I think there are several ways, but I would just want to see, can we make it this way? So we are going to have 1/sine. So 2 1/sine 3x, or this is ln, right? So 1/u du. So we can have 2 ln u or ln sine 3x, or this is let me write here. So integrating factor is e ln sine 3x and then squared like that. And we could write down that the we can cancel e and ln, right? So we can write sine squared 3x, okay? Right? Okay. So we can multiply, let me write this here. So we multiply the sine squared 3x. So what? W prime sine squared 3x plus 6. This is cosine 3x over sine 3x, and then sine squared 3x w equals 0. So we could cancel this one, and then we can simplify, take into our product form w and I think sine squared 3x, right? Now we can make sure if we derive this will be going to be 6 and 2 and then 3, 6 cosine 3x and sine 3x. Okay, now we take the integral. Then this will be sine squared 3x w equal to the constant. Okay, now we know that our w is u prime, so sine squared 3x, u prime is a constant. Okay, so u prime is a constant and multiply with 1 over sine. 1 over sine is cosecant, so we can write cosecant squared. Or if you want, maybe just 1 over sine. 1 over sine squared 3x. And then we need to integrate this u prime. Okay. So it's become u. And integration of sine squared, 1 over sine squared, or integration of the cosecant squared 3x dx. So 1 over sine squared, what will be? Anyone? I think you can just use substitutions, right? Okay. Or if you have the table for the integration, this will be equal to the cotangent. Multiply with a constant. So let me write here. This will be another constant. Let me write C1 and then cotangent 3x. So y2 is C1 cotangent 3x. Or we could say, because C can be any constant, so let me just write u as cotangent 3x, multiply with the sine 3x. So this is u, this is y1. So our y2 is cosine 3x. So you need to remember that the constant in our case is not really significant, because we know that the constant just changing the scalar multiplication, which is, we already learned that is the linear dependency, right? So we want to make it linear independent. So we only care about the function itself. So the constant is not really that we like taking much care. We just focus on the structure on the function, because constant can be any number. So we're only interested in this cotangent 3x. So we propose that, okay, that y2 is the cotangent 3x multiplied with y1. So the idea of reduction order is we need to reduce the order of the second order to become first order. Find the u, and then use that u in y2. And to make it complete, the requirement, it needs to be second order, and it has y1. So it has another solution. If one of them kind of missing, then we cannot use this method. Okay? Equal and forget to write a constant. Let me. Oh, should be negative. Should be negative. But we don't have any interest in the constant, the negative, positive. We only care on the function. I believe the second one will also start with the same thing. Okay, you can try for the second question. We can try to find u. Okay. We try to propose the y equation is u multiplied with e to the x. And then differentiate twice, put here, and we have a new equations. Okay. So first we can deal with the y is u x and then e to the x like that. And it goes through the first derivative. And then second derivative. Okay, so we can write u double prime e x plus 2 u prime e x plus u e x like that. Now we need to be careful. Plug in all the information. Okay, notice that in the previous examples, or we already checked from last week also, the last example from before this one is equal to 0, right? Which is the homogeneous, right? Homogeneous. But here we are having some structure on the right side, which is this is non-homogeneous. What will be the difference? In non-homogeneous, the answer or the solutions that we are going to have is we have yc and yp, right? We have the complementary and then particular solution. That will be appear in our solution at the end. So we need to identify which one is our particular solution, which one is the y2. So y2 is y1, y2 is kind of, you can say it's homogeneous, and then yp is something that is added, okay, added after that. Okay, we can look on those at the end. But first, let's try to solve this. Okay, so let me start to write this down. So 2u prime minus 3u prime is minus, right? Minus u prime ex like that. And the other part is u minus 3 is minus 2 plus 2 is 0. Okay, so 0. So we are going to cancel this, and this. Okay, and this will be equal to 5e with power of 3x. Okay, and usually if you check the textbook, try to work out the practice in some exercise. Maybe later I will also give you perhaps not a homework, but maybe just some exercise. You will see that even though we have like really long substitutions, the textbook already said that some of the object inside will be cancelled. Okay, so it will be more simplified. Okay. Okay, now we are going to reduce this. So try w is u prime. So this will be our new expression. So this will be w and then ex and then 5e 3x. Okay. And again, this is linear, right? This is linear differential equations. So we could take this and find the integrating factor. It's e with power of, or maybe let me make the writing. Let me make the writing goes here. So this will be w. So we divide with e to the x. So we have 5 e and 2x, right? Okay, I think this will be clear enough. So we have the integrating factor is negative dx, or we have this will be e negative x. Okay. So we multiply with e negative x, and this will be x. Okay. And we find the product form from this is e negative x, precisely the same like that. And this will be 5e to the x. Okay. Okay, let me move this to here, that w e negative x is equal. So we integrate, so 5 ex plus, let's say c. Okay, let's say c. And since w is u prime, so we can write u prime e to the negative x is 5ex plus c. So u prime is 5e to x plus, let's say this becomes c1 ex, or rather just c is still okay, I think. And then we integrate, so u prime becomes u equal, this will be 5/2 e to 2x plus c ex plus c2. Or maybe write c1 here to make it have two constants. This is u. But we need to find the y. So y is u y1. So 5/2 e to x plus c1 ex plus c2 multiply with e to the x. So we have 5/2 e 3x plus c1 e 2x plus c2 ex. Okay. Now we have these expressions. Our goal now is to identify which one is our homogeneous one, which one is the particular solutions. Remember that y1 is e to the x, right? So we could say that since y1 is this, then this will be y1, right? And which one is y2? Which one is y2? This having two constants. So this is y2. Remember the structure, like I think last week? We have a constant function. That will be our yc, the complementary solution. So this will be y2. And this will be yp, okay? The particular solution. Okay. You can check the introduction of the higher order to find the same structure with this. Like we have the C1 and then Y1, C2, Y2, or this right is 2, but it's actually just a constant, so nothing really matters. But the important thing here, we need to identify at the end, okay? Especially for the non-homogeneous one. For non-homogeneous. For homogeneous, the answer will be directly the solution itself. But for non-homogeneous, we need to identify. Sometimes the question is asking what will be the yp, and we need to identify which one is our yp. Okay. Okay, any questions? Any questions? Yeah, I think either separable or a linear from the first order, we are going to use frequently also in the higher order, especially for the reduction of order. For reduction of order, we are going to see linear method quite often. Is it too small? Is it too small for you? It's okay. Okay, let me continue. Okay, now we are moving to the next techniques, okay, the next method. It's called the constant coefficient. This is within the homogeneous linear equations. Okay, remember that when we have differential equations, let's say y prime plus, let's say a constant, y equals 0, a is constant, it will possess, the solution is an exponent, right? Exponential. So we have usually y equal to, let's say, c1 and then e with power of maybe negative ax, like that, right? And this is quite true because with e, when we derive, no matter what power this e will bring, we are going to have its original expression in its derivative form. So when we deal with this differential equation, it seems that the solution makes sense to make it equal to 0, right? Okay. Now from here, we could also think that when we have the general expression, let me write the general forms for the higher order of dE. For homogeneous, we can think that solution are either exponent or constructed out of exponent. Exponential functions. So exponential will be very, very important in our explanations. Okay, to begin with this method, let me just write down some general form. So consider we have ay double prime plus by prime plus cy equals 0. And let the solution in the form of y with e with power of mx. Okay, let's solutions with this y. So first, as usual, we try to differentiate. So m is a constant, and differentiate with another one. It will be m squared e mx. Okay. Now we have, maybe we use blue, a m squared e mx plus b m e mx plus c e mx. This is equal 0. So we simplified, factor the e. Okay. Now since e, this is always positive, right? The function is always positive. The one that makes 0 is this expression. Okay? The am squared plus dm plus c. Okay? All right. This is called, we call this auxiliary equation. Okay, this is like a usual quadratic functions you already learned previously. So we are going to have roots, right? Roots m1 and m2. Okay. And we are going to identify the root from discriminant. Okay, if you remember this discriminant. Okay. Let me write the quadratic formula is right. Now the one that under the square root will be identifying our roots, whether it is real, it is imaginary complex, okay, or it's just we are going to have equal to 0. It is also okay. So there will be three case based on discriminant, or discriminant is the b squared minus 4ac. Okay. So if the discriminant is positive, so first case b squared minus 4ac is positive, then m1 and m2 will be real and distinct. Distinct means they are different value, okay, different numbers. And then you can also have the case when it's equal to 0. So this will be m1 and m2. They also real, but they will be equal. Okay. And in the third case is when it is less than 0. And the roots will be a complex or conjugate complex. Okay, let's break through our case by case for these three cases. So in the constant coefficient, before we deal with the solutions, we can first identify the case. I think we can have break. After the break, we can continue. Zoom out. Here. Too small or?
Time limit, I get ready to go.
Okay, we continue with some three cases here. The first two will be easy to follow, I think. The third case is somewhat a little bit confusing and well, you could see first what it is. Okay. I think I will give you the first two. So the case 1. So let's say the solutions, let's say it will be m1x, and then y2 is e m2x. Okay. Now these functions, they both should be linearly independent on interval, on all interval, okay, on all x, and we can write the general solution. Okay, nothing really complicated here. Let me describe all the case first, and then we can see some example. So case 2. Well, we call this, let's say, distinct real roots. The first one, I forgot to mention. The second one is repeated real roots. So it only has the one solutions, let's say e power of m1x, like that. And from the quadratic equations, so since m1 is equal to m2, and b squared minus 4ac is equal to 0, then our m is negative b over 2a. Okay. That's to determine the our m here. So we need to also mention what will be the for the second y. To define the y2, we are going to use the formulation from the reduction order with y1. So y1 So this will be E m1x, and then integrations, and then E with power of the P it's 2m1x, and then E 2m1x dx. So we get E m1x integration dx, or this is x E m1x. Okay, the 2m1 is from here, okay, from this to go here. So we have the 2m1 or p. So we need to divide by a, right? And then we can write. Or we could, well, let me just write that the negative b over a is 2m. So the solution, so the general solution is y equals C1 em1x plus C2 xe m1x. Okay. And this will create a pattern that we will going to see through later. When we deal with, for example, we have one solution E mx or m1x. If it is having the same roots with this auxiliary equations, then the second solution is having x. And later, when we have more than, this is just having two roots, right? When we increase the order, we might have 3 or 4 or 5. But when it's still with the same conclusion here, that this discriminant is 0, or this solution should, or the value should be the same, we will have x e mx, x squared e mx, and so forth. Okay? As long as it is linearly independent. We will going to see through that later. Okay? So this is the second case. Now the third case, case 3, is the conjugate complex roots. Okay, M1 and M2 are complex. So we can write M1 with alpha plus imaginary number beta, and M2 is alpha minus imaginary number beta, with alpha and beta are real coefficient. So alpha and beta is greater than 0 and real, and the imaginary number squared is equal to -1. We can write the complex is the same with the first case, but we are just changing the M1 and M2. So E, this will be alpha plus beta, or plus imaginary number beta, sorry, x, and then plus C2E alpha minus imaginary number beta x. Okay, however, this form is not really practical. We are going to elaborate this power with the Euler formula. Okay? If you're still not sure what that is, perhaps I will give you just additional supplement, another explanation from. Well, I will find video that's suitable for our lecture. But let me just explain this expression. Okay. So consider Euler's formula that is E with power of imaginary number theta is equal to cosine theta plus I sine theta. Okay. So if we have E and then we have imaginary number beta, let's say beta x, from our expressions, okay, this will equal to cosine beta x plus I sine beta x. Okay, and then we have also the negative imaginary number beta x. This will equal to cosine beta x minus I sine beta x. And remember that in trigonometry, in the observations of the quadrant, when we have cosine at the negative angle, this will be a positive, right? And in the quadrant 4, right? And for sine, it will be negative. Okay, if we add these two, this will cancel, right? So we could write down E this will be 2 cosine beta x, and if we minus this, will be minus is plus I, so 2 I sine beta x. Okay. Okay, let me write and copy all this into a new page. Let me copy here. And copy this one. Copy around here.
Now look at the general solutions, the same here. So we are going to, now we are going to have C1 and C2 with many numbers that you can choose, and to make it simplified, by looking at these terms, when we have this plus and this minus, let's say we are going to have our C1 and C2. First is maybe that let C1 and C2 is equal 1. So we can have this expression. So we can plus the E both together. So let's just do that.
So first let C1 equals C2 equal 1. Okay. So we are going to have, first is one solution. That is E, let me write completely, not A, alpha. Okay. And then,
to make it the second expression here, we are going to have negative. So C1 is 1, C2 is negative 1. So let's try that one.
and then let me write here. So let C1 equal 1, C2 equal negative 1. So we have Y2 is E and minus. Okay, now we have these two proposed solution for Y1 and Y2.
Now looking at this
Y1, we could take the expressions out of E alpha x, and we have E imaginary number beta x plus E negative. Okay, and this will be, it turns out this is going to have 2 E alpha x cosine beta x. This is from this one, from the one on the left here. Okay. And Y2, the same way, we are going to have E minus, and this will be 2 imaginary number E alpha x sine beta x. Okay. And now from this
Y1 and Y2, we could rearrange our general solution. So this Y1, Y2.
so we could arrange the general solution. So general solution. This is Y. We could write with constant 1 E alpha x cosine beta x plus C2 E alpha x sine beta x, or this is equal to E alpha x C1 cosine beta x plus C2 sine beta x. the problem now is how to apply this in the practice way, in the practical problem. We're going to look at the example. Remember that alpha and beta, we are going to get those expressions from the complex root. So we are going, first, every time we have this type of question, we are going to look on the auxiliary equation. The auxiliary is using the m, okay, the m squared plus something, and we need to define the roots from there, whether it's distinct, it's equal, or it's going to have a complex. When it has a complex, usually for complex, usually you have some real numbers plus minus with the square root. The square root, it might be an imaginary number. Okay? So that will be alpha, and the one that's inside the root, that will be a beta. Okay? Usually that's how we identify. But let me just go through examples. How many times we have left? Okay, maybe example for the first two, and maybe the Thursday we can have example for the last one. Okay. Okay, let me go through examples. So let's say we have 2y double prime plus minus 5y prime minus 3y equals 0. Okay. The first step is to imagine an auxiliary equation before we decide that the constructions for the solution will be based on exponential. Okay. So the y will equal to exponential something. So basically, to summarize, we can treat this second order, the y double prime, y prime, and y, exchange directly to m. It will be somewhat equal. So we could use auxiliary equations and write down a quadratic function that is this. Okay? Because we know that we can factor out this e outside, and we are left with the this auxiliary. Okay? And then we are going to determine our m. Okay? M1, M2. So try your best. Can we factorize? Can we use something here? I think we can factorize, right? If you're still not familiar to factorize, you can use a table like this. Okay? So 2m squared is based on m and 2m, right? So write down the possibility. So 2m and m, right? And the right side -3, maybe 3 and -1, or -3 or 1. Right? But when we cross multiply, the result should be -5. So I think this will be negative, and this will be positive, because we are going to have negative 6m plus 1m, which is -5. Okay? So we are going to have 2m plus 1 and m minus 3, okay, equal to 0. So m1 is -1/2, m2 is 3. Okay, I think this is the case for the first one. Okay, this is having distinct real roots. Okay. So this is distinct real roots. So we are writing the general solutions. Y, C1e with -x/2 plus C2 e with 3x. Okay. So number 2, this is for the second case. Let me write you the equation first. And the same way, we could exchange directly the double prime with the m squared 4m plus 7. Okay. Sorry. This one for the third one. So this will be here. The second one is different. Okay. So the second one is this: y double prime negative 10 y prime plus 25y. Okay, we could directly write this with auxiliary equation: m squared negative 10m plus 25. And we can factor, right? We can factor that this will be the solution. So m1 is equal to m2 is equal to 5. So we are going to have the general solutions y c1 e 5x, and the second one will be c2 x e 5x. So this is the general solution. Okay, the third case, this one. Now same thing, we could write this with the auxiliary equations. Okay. And notice that I already prepared that we cannot really factorize this directly. So there are two ways. You can directly use the quadratic formula, or you can complete the square to find the m1 and m2. So let me write the complete the square. So we're going to plus 4 and plus 4. So we are having m plus 2 squared, and this will be equal to negative 3. So we have m plus 2 is square root of negative 3 plus minus. So we have m1 is 2 plus, or negative 2 plus square root of 3i. Maybe this should be like this. And m2 is negative 2 minus. Okay, so this is the alpha, and beta is square root of 3. Now to write down the general solutions, we could use the e with power of alpha x, right? E, alpha is negative 2, so negative 2x. And write down all the cosines beta x, and then plus sine beta x, like that. And of course, the questions can be also elaborate with the to find the constant. If we have the initial value from, if we have the initial condition, then we can apply the initial condition and find this constant, and we can find the real solution. Okay, any questions? Okay. I will give you one more. So this is practically for the auxiliary equations. It should be the second order. So let me give you the, if we have the higher order. If we have higher order. So the roots, since the root is just having m1 and m2, right? Just two. But we can have more actually. We can have more. We can also by the same, I think the same principle. I will just give you the last one for this session. So the last one is the higher order equations. I think for Thursday we can have more examples. Okay. So to solve nth order differential equations, we must solve n order or nth degree polynomial equation. So we can exchange the order with m, and the auxiliary equation becomes long. Okay, so this is the order, and this is the auxiliary. So we exchange this y order n becomes m with the power of n. Okay, so if all roots are real and distinct, then general solution is y equal c1 e m1x plus c2 e m2x plus cn e mnx. But it is more difficult if we try to summarize the case 2 and 3, because the roots is greater than 2. Okay? The roots is greater than 2. Like if we have 5th degree, well, we could have 5 distinct real roots, or maybe 3 real and then 2 imaginary complex. That's also possible. I think I also mentioned that, if you remember, when we deal with the polynomials, we could have like possible roots.
possible zeros, possible roots, right? So for case 2 and 3, it's difficult to analyze. But if we think on if m, if let me write, if m1 is root multiplicity, which means it's going to have another one that is having the same root multiplicity of k of n degree auxiliary equations, then solutions that is linearly independent this will be equal to E m1x and then x E m2x as I mentioned before. And if we have more than 2, like say 3 or 4 and maybe more, then it will be multiplicity of the x. Okay, so this will be x squared E m3. Oh, sorry, it's just 1. It's this multiplicity. Sorry. This should be 1, 1. Okay, and then x n minus 1 E m1x. Okay, if m1 is having multiplicity. Okay. So general solutions, when we have this, is y equals c1 E m1x plus c2 E x E m1x plus, let's say, c3 x squared E m1x and plus ck, let's say ck x k minus 1 E m1x. Okay, we continue the examples later on Thursday. So I will stop until here. And for this case, of course, we don't really much think on the complex, actually, because from general solution, usually we are going to have a real solution. But there will be some cases that probably we are going to include the imaginary number, but we will talk that later on. Okay. So we can combine. If we have real distinct, and maybe the other part is having same root multiplicity. So maybe we have 5, m1 maybe having with m2 the same thing, same root. So we are going to have this combination for that too. Maybe the other one is different roots, real, like the first one, and the other two maybe is complex. And we are writing the same thing as previously with cosine, sine, something. So yeah, we could have like long. Okay. So I will stop it here, and we are going to have more examples on Thursday. Before that, as usual, I prepared just one question for feedback. Okay. So, have you finished the notes? Or do you still want to write? Okay, if you finish, then we are going to go to feedback.
Just one question about reduction of order. I think you should be able to be finished on maybe a couple minutes if you directly get the answer. So for this chapter is actually we have reduction of order, the constant coefficient, the undeterminate variation of parameter, and Cauchy. So five techniques. We are going to have midterm after we already get this fine. That will be the midterm. So we are going to have more exercise first. Maybe quizzes first. But if we don't have time, then the quiz will be maybe online. If we don't have time in class. Okay. Okay, please write your student ID. Okay. I think we can start. Okay, hopefully 4 minutes, 4 minutes and a half is enough. You have the homogeneous, you have the y1. Well, if you want to try using the direct formula, also okay. Okay, also okay. But I suggest you just using the sum. But if you could just using the y2 equal y1 and integrations e with power of negative p over y1 squared dx, also okay. If you think that maybe it's too much the integration, then I think this one may be easier, but long writing. This long writing. If you find some flaw in my questions, then you can also find the answer. I think that's okay. Okay, that's okay. Yeah, I forgot to check. So yeah, it's flaw in my question. Yeah, so Rion already knew what is the flaw. I think some of you already know also what is the flaw in my question. Not the question in the options. There's a flaw in the option. If you careful enough, you can get the answer directly. Originally there is two questions, but I reduced it become just only one. Yeah, you can check, right? You can check. You can check. You can check the option. Who is Ronald? Ronald? Okay. Okay. This is for attendance, and well, this is the end of our lecture.